Hello and welcome to Empowered Learning. This particular lesson will be on Pascal's triangle and how Pascal's triangle relates to computing the combination of n things grouped r at a time. So in short, this is what Pascal's triangle actually looks like. We're going to show you how to construct that a little bit later, but for right now we just want to focus on where does Pascal's triangle come from, what does it actually compute, and then we'll sort of make that connection here later. So Pascal's triangle is just a triangular array of numbers where they actually compute the coefficients of what's called binomial expansion, okay? And so here, if we take a binomial x plus y and raise it to the power of n, then and actually multiply that out, that's what's called binomial expansion. And to show you that this particular array of numbers here actually computes those coefficients, I'm going to do a simple example. So let's say we have x plus 1 squared, okay? So we all know that x plus 1 squared is the same as x plus 1 times x plus 1. And then when we multiply that out, you know that we end up getting x squared plus x plus 1, which gives us x squared plus 2x plus 1, okay? If you notice, here in the row 2 for Pascal's triangle, we actually have the 1, 2, 1 that appears here, okay? And so that's what we mean by when we see this thing, combination of n things given r at a time, they're actually computing these coefficients that are here, okay? So next what we're going to do is show you how we actually construct this particular Pascal's triangle and then make the connection in between the two. And then we'll finally end up doing some examples where we take some combinations of things and use Pascal's triangle to evaluate them versus us using a calculator or doing it by hand, okay? All right, so let's go ahead and get rid of this right quick. And so now what we want to do is talk about actually constructing Pascal's triangle. Now, it's rather easy to do. The first thing that we have to do is we start off with a 1 here, and then we start off with a 1 here and a 1 there. Now, after that, from, let's say, row 2 onward, what we do is we start and stop each row with a 1, and then any numbers that are in between, we add the two numbers that are above it to get what that number is supposed to be. So as an example, here, we start the row with the 1, we have 1 plus 1 is 2, nothing left, so we end with a 1. We go to our next row, begin with a 1, 1 plus 2 is 3, 2 plus 1 is 3, and we end with a 1. We go to our next row, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then we end with a 1. Keep on doing it again. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then we end with a 1. And so we'll do one more row here. So we have 1, 6, 15, 20, 15, 6, and 1. And as you see, this goes right along with rows 0 through row 6 here. And so when we do this, we actually do start off with row 0, and I'll tell you why in just a second. So we know how to construct Pascal's triangle now. Now, what it turns out, just like I showed you with the formula for the binomial expansion for the binomial coefficients or whatnot, it turns out that this particular 1 represents the same thing as the combination of 0 things taken 0 at a time. This 1 represents the combination of 1 thing taken 0 at a time, and this one represents the combination of 1 thing taken 1 at a time. I'm going to go ahead and erase all these pluses here. So if we keep that pattern going, you'll see that row 2 represents a combination of 2 things taken 0 at a time, 2 things taken 1 at a time, 2 things taken 2 at a time. Next row, combination of 3 things taken 0 at a time, 3 things taken 1 at a time, 3 things taken 2 at a time, and 3 things taken 3 at a time. And our next row, combination of 4 things taken 0 at a time, 4 things taken 1 at a time, 4 things taken 2, 4 things taken 3, and 4 things taken 4. And as you can see, we could keep going on and on and on and on and on, okay? So knowing that we have this connection in between the combinations and Pascal's triangle, we can use that as an advantage, of course, if you actually write this out for yourself, to be able to compute combination type expressions instead of using your calculator or factoring out factorials. And so I'm going to do a few examples just to sort of show you how this could actually really help you out, okay? All right. So we look here and let's say we have this particular example. So let's say we do the combination of 6 things grouped 2 at a time. Well, normally what I would do is just say 6 factorial divided by 2 factorial times 6 minus 2 factorial. But here, since I have Pascal's triangle and I have it up to at least row 6, I don't have to do that anymore. So what I can do here is just say, all right, here I want to go to row 6 and find where 6 things taken 2 at a time. And so if we look at row 6, this is understood to be 6 things taken 0 at a time, 6 things taken 1 at a time, 6 things taken 2 at a time. So the answer to this is actually 15. Now, if we did this the long way, you'll see that we still end up getting the same answer. And I'll go ahead and work it for you just to show. So this will be 6 factorial over 2 factorial is just 2 times 4 factorial. And so 6 factorial is 6 times 5 times 4 factorial. And now you see the 4 factorial is reduced to 1. We have 2 going into 6 3 times, and we end up with 15. So you see it's the same thing, but once you have this written down one time, you can just map and go directly to it without having to do all of this, okay? Let's do one other example. So let's take the combination of 7 things grouped 4 at a time times the combination of 3 things grouped 1 at a time times the combination of 5 things grouped 2 at a time, okay? So again, for here, instead of writing out the factorial version of this, this, and this, we'll just read Pascal's triangle, okay? So if we read Pascal's triangle, we want row 7, and we're going to get in the 5th spot, because remember, we're starting from 0, so 0, 1, 2, 3, 4, 5, so we'll have the 5th spot. So row 7. 7 things group 0 at a time, 7 things group 1 at a time, 7 things group 2 at a time, 7 things group 3 at a time, 4 at a time, 5 at a time. So we know that combination of 7 things group 4 at a time is just 21, okay? If we do the combination of 3 things group 1 at a time, we start with row 3, 3 things group 0, 3 things group 1. So that ends up being 3. And of course, 5 things group 2 at a time, we go to row 5. 5 things group 0, 5 things group 1, 5 things group 2. So we have 10 there. And so now when we put this all together, of course, this is going to be 63 times 10, which is 630, okay? And so, as you can see, this is much faster than actually doing the factorial form for all 3 of these.